So for the IB syllabus, here's what we're expected to know about parallax. One, you got to be able to define what a parsec is. We'll do that today. Two, you should be able to describe the method of determining distances to a star using stellar parallax. We'll talk about that today, and we'll actually practice it with a little lab. You should be able to explain why the method of parallax is limited to measuring stellar distances less than several hundred parsecs. You should have an understanding of why that is true. And finally, you should be able to solve problems involving parallax. It's relatively simple once we get into it, so let's get into it. Okay. First of all, you should have a pretty firm understanding that there's a lot of empty space in space. Space really is just space, really, really empty. And it's so far and so distant, we usually, so far and so empty, we usually measure distances with a unit called a light year. Please understand that a light year is not a measurement of time. It is a measurement of distance, okay? It is the distance that light travels in 1 year. Now, light is really, really, really fast, right? 186,000 miles in a second. So the distance it travels in a year is a light year. It's approximately 7.5 trips around the Earth in a second. Okay, that's how fast light goes. 7.5 times around the Earth every second. Multiply that by how many seconds there are in a year. That's a light year. Okay? You do not need to memorize this number, that a light year is 9.46 times 10 to the 15th meters. You have it in your data booklet, but that is how long it is. It is an extremely large distance, but it is very useful in astronomy because we're usually talking about extremely large distances. To give you some bearings, the Earth and Moon are about 1.3 light seconds apart. Okay, 1.3 light seconds. You shoot a laser beam at the Moon, 2.6 seconds later, you see the flash, if there's a mirror up there, which there is. And so that's one of the things that that NASA astronauts did and allowed us to measure very... let's see what else here. Okay, so the Earth-Sun distance is about 8 light minutes. It takes a little bit more than 8 minutes for light to get to us from the sun, which is about 150 million kilometers or 93 million miles. Again, just kind of some things to think about. Our next closest stellar neighbor, Proxima Centauri, about 4.3 light years away. So to get to the first star, you have to be traveling at the speed of light for a little over 4 years. That's about 10,000 times farther away than Pluto, just to give you an idea. And in order to get to the center of our galaxy, again, the Milky Way galaxy, hundreds of billions of stars, it's about 30,000 light years away. We're still within our galaxy. We're just, that's just to the middle of our galaxy alone. We're talking 30,000 light years. It's about, the Milky Way galaxy is somewhere on the order of 100,000 light years across from side to side, okay? Just like they talk about in the song. And again, to get to our next closest neighbor, the Andromeda galaxy, you're looking at 2.2 million light years. So once we get out to galactic scales, we're talking millions of light years away. That's a close galactic neighbor. And then as you go farther than that, obviously there's many, many, many more galaxies. So how do we measure these things? Well, let's look at the close distances first. This is a technique we use to measure stars within the Milky Way galaxy. Okay, we don't use this technique to measure other galaxies. This is just to measure nearby stars within our galaxy. And it's called parallax. And parallax works something like this. Something like this, okay? If you close one eye, okay, and hold out your thumb and aim it at a target, aim it at a distant target, and now switch the eyes. Keep your thumb in the same place and switch your eyes. Open, close. Notice your thumb moves back and forth, okay? If you could measure how far back and forth it moves and how far away it is, how far back and forth it moves and how far apart your eyes are, you can measure how far away your thumb is. Notice that when you do the same thing and the thumb is closer, do the same thing and bring your thumb closer. And notice that your thumb moves much farther. Farther away, the thumb moves much less. That is parallax, okay, that idea. And it actually, you use it all the time. It is how your brain does depth perception. When you're driving in a car, things are whipping by really fast. Those are close, okay? Things aren't whipping by. Those are far, okay? And a lot of times that's how it works. So in terms of measuring distances to stars, here's how we use parallax, okay? This is a diagram that you probably want to understand. Notice that the Earth is going around the sun. There's stars. Some are close, some are far. The ones, some are young, some are very, very bad. Go ask your dad. Okay, so the stars that are closer to us will appear to move relative to the stars that are farther from us as we orbit the sun. Just like when you changed your position with your eyes, your thumb moved back and forth relative to the distant background. stars do exactly the same thing. There's two ways we can use parallax. We can actually use parallax on a daily basis for things that are really close, like planets and stuff like that, because you could observe it over here, okay? And then as the Earth rotates 12 hours later, you could observe it over here, and notice you've moved that far away, and you can see how much it wobbled and measure its distance. That's one way to do parallax. Usually when we're talking about stars, what you'll do is you'll observe the star at one point. 6 months later, so this is June, this is going to be December, you'll look at that same star again. Notice that the Earth has moved a great distance. This is like changing your eyeball. And the star will also have appeared to move relative to the more distant background. Knowing this distance and knowing this angle, we can measure this distance, okay, using trigonometry. So, okay, here we go. Oops. Okay. See how as the Earth is going around, notice the red star in this image is moving much farther than moving back and forth much more than the background stars. If you can measure this angle, how far it's moving back and forth, and you know the distance, the diameter of the Earth's orbit, then we can do some calculations and measure how far away it is, okay? So the idea of parallax, okay, is using that apparent motion of a close star relative to the background stars. That's what we'll do. And let's take a look. So here is the geometry of what we have set up, okay? This is the sun. This is the sun here. Here's the Earth. It goes around the sun. And we take two measurements. There's our star. Notice that if I can find this angle here, okay, and I know this distance. What is the distance from the Earth to the sun?
1 AU.
We're going to call that an astronomical unit. 1 astronomical unit to make our lives easier. 93 million miles, but 1 AU is one's a lot easier number to deal with. Notice I have a right triangle. Ding, ding. And I want to know this. What trigonometric function will I use? Tangent, because we're doing opposite over adjacent, right? So tangent of my parallax angle is equal to opposite, which is what? 1 AU over adjacent, which is the distance I'm looking for. So I can rearrange this to say, hey, the distance I'm looking for is 1 over the tangent of the parallax angle. Now there's something really, really cool about this. This angle, these distances are so great that that angle is going to be incredibly small. Incredibly small. It's going to be less than a 60th of a degree, which we call a minute. It's even going to be on the order of a 60th of a minute, which is a arc second, okay? So that when this angle gets so small, you can forget about tangent. Our life becomes super easy, because when that angle gets so small, the tangent of the angle is the same thing as the angle. It's weird. You can try it if you want, with really small angles. So our equation becomes the distance to the star is just equal to 1 over the parallax angle. So easy, okay? So what we were just looking at, you can see that, we did the trigonometry. The distance to the star is equal to the radius of the Earth's orbit, okay, which is going to be 1 because we're going to use astronomical units. And then that angle is a parallax angle. But here's the trick. In order for that tangent to disappear, we're going to be measuring that parallax angle in arc seconds, in 3600ths of a degree, okay? Because 1 minute is 60th of a degree, 1 second is a 60th of a minute. So 1 arc second is 1 3600th of a degree. It's a very, very small angle. If you use an angle in arc seconds and you use astronomical units for this r here, so you put 1 up there, you will get the distance in parsecs. That's why we use parsecs. Kind of nice. Makes our math super easy. All right? So let's look at that more specifically and talk about parsecs. Okay? By the way, you guys, this method, this technique, is really only useful up to about 100, I think actually now maybe up to 150 parsecs away. Why would that be? Exactly. We can't measure angular parallaxes for things more distant than that. So this is a great technique for nearby stars. We've actually launched, the ESA launched a satellite in the late 80s, early 90s called Hipparcos, which was solely designed to measure parallax angles better than it had ever been done before. and it measured the parallax angles of like 120,000 stars. And so we got really good distance measurements to about 120,000 stars, that are all within about 100, 150 parsecs of Earth. Right. So what the heck is a parsec? What the heck is a parsec? This is one of the things IB expects you to know, is what a parsec is. And the word parsec stands for parallax in seconds of arc, or parallax in arc seconds. Bless you. So when we use our equation, d equals 1 over the parallax angle, d will be in parsecs. You will get a distance in parsecs if you use that angle in arc seconds. The definition of a parsec, here's the definition of a parsec. It is the distance away from Earth where 1 astronomical unit, I guess it doesn't have to be from Earth, the distance away from anything where 1 astronomical unit from your vision would equal 1 arc second. It would subtend an angle of 1 arc second. So if I take 1 astronomical unit, the distance from the Earth to the Sun, and I start moving away, moving away, moving away, it's going to look smaller and smaller and smaller, right? At some point from my vision, it's going to be so small that it only takes up 1 arc second, 1/3600th of a degree. At that distance, I am 1 parsec away. I'm 1 parsec away from that astronomical unit when it is only the size of an arc second. Here we go. So 1 parsec is the equivalent of 3.26 light years. 3.26 light years. And this conversion factor, I believe, is in your data booklet, so I don't think you have to memorize it, but there will be times where you'll need to convert between parsecs and light years. But our math using parsecs and the parallax method of distances is quite easy and quite nice. So just for fun, let's check it out. Okay? In 1989, they launched this Hipparcos satellite to conduct a massive survey of like 100, 120,000 stars. The smallest parallax angle that this satellite could measure was 2 milli arc seconds, okay? Or 2 1,000ths of a second, or 2 1,000ths of 1/3600th of a degree, okay, of your pinky at arm's length. That's really a small angle, and it can measure them. So please calculate how far away it could measure, what the greatest distance it could measure using parallax, assuming that it was orbiting with the Earth. We're using 1 astronomical unit. Let's figure out how many parsecs away it could measure and how many light years. All right, Proxima Centauri, 4 light years away. Please tell me the parallax angle of that star. As we go around the sun every 6 months, how much does Proxima Centauri wobble? What's its parallax angle? All right, let's try one more. How far away is Sirius? Has a parallax angle of 0.3705 arc seconds. Sirius is one of our nearby neighbors. That's why one of the reasons why it's so bright. Okay, 8.8 light years. Good. Easy math, you guys. Easy math. Excellent. Okay, let's talk about. That's it.